Howdy class. So today we're going to be talking about percent composition of compounds. I want to apologize. At one point during my lecture, I might have mentioned that we were going to be doing um, combustion analysis, and I was wrong. I thought that fit into this chapter, but it does not. So anyway, this is a lot simpler than that, just basic percent composition of compounds. So let's get started. All right, so molecular formulas, you guys should know what molecular formulas are now. They tell us the amount of each element present in one molecule of the compound. So for example, a molecular formula would be like water. H2O has, this is a molecular formula. It tells us that there are 2 atoms of hydrogen in one molecule of water and 1 atom of oxygen in one molecule of water. So let's look at a little more complex molecule. So acetic acid, which is also known as vinegar. So you know acetic acid, I'm sure. One molecule of acetic acid contains 2 oxygen atoms. It has other things, obviously, but we're going to start with those oxygen atoms. So this is acetic acid. This is its structural formula. This is a molecular model of acetic acid, and it has 2 oxygen atoms. I'll circle those. Those are the red ones on the molecular model. So one molecule has 2 oxygen atoms. If we multiply both of those numbers by Avogadro's number, that tells us that 1 mole of acetic acid contains 2 moles of oxygen atoms. A mole is just Avogadro's number worth of molecules or atoms. It's just a multiple. So we have 1 mole of acetic acid, and in that mole of acetic acid, we have 2 moles of oxygen atoms. Therefore, the molecular formula can be used to determine the amount of an element present in any sample of the compound. So not necessarily 1 mole, but however many moles you have, you can use the molecular formula to determine the number of moles of the element that is present in that sample. So, for example, let's look at this. Find the amount in moles of each element and the number of atoms of each element present in 1.2 moles of acetic acid. So I'm going to let you guys work on this. So you can pause your video and work on it now. And then I will go through the answer here for us. All right, so this is our structure for acetic acid. So I'm going to go ahead and write out how many atoms we have of each element in our compound. So we have 2, we know we have 2 oxygen atoms from the previous slide. What else do we have? We also have, those are those 2. We also have 2 carbon atoms. And we have 1, 2, 3, 4 hydrogen atoms. Okay. So that's how many atoms we have in one molecule. So now we want to find the amount in moles of each element if we have 1.2 moles of acetic acid. So just like we did with the oxygen on the previous slide, we saw that there were 2 moles of oxygen atoms in 1 mole of acetic acid. So that is a conversion factor. If you remember back to dimensional analysis, that is a conversion factor. 2 oxygen atoms in 2 moles of oxygen atoms in 1 mole of acetic acid. We're going to have, that's our conversion factor for oxygen. We're going to have the same conversion factor for carbon and hydrogen. Similar, at least. So 2 moles of carbon in 1 mole of acetic acid. Sorry. And 4 moles of hydrogen in 1 mole of acetic acid. So we have more hydrogens because there are more hydrogens in 1 molecule of acetic acid. All right, so those are our conversion factors. So this is what we have to start with. So if we have 1.2 moles of acetic acid, not just one anymore, but 1.2, then we can multiply that by all of our conversion factors. So 2 moles of oxygen for 1 mole of acetic acid. I'm going to call it AA. Those are my initials, as well as acetic acid's initials. So 1.2 moles of acetic acid cancel out, and we end up with 2.4 moles of oxygen in that sample of acetic acid. Likewise, we're going to have 2.4 moles of carbon, because we have the same conversion factor, 2 per mole. So 2.4 moles of carbon is in that sample. And we have 4 moles of hydrogen, so that's just going to be 4.8 instead. So 4.8 moles of hydrogen. So those are the amounts in moles of each element present in 1.2 moles of acetic acid. So there you go. What else can we do with these molecular formulas and their molar masses? So molecular formulas can be used to determine the percent composition of an element in a compound. So just like we can find the relative, or we can find the exact amounts of each element in a certain sample of a compound, we can find the percentage of that element in that compound. So the percent composition of a compound is the percentage of the total mass contributed by each element in the compound. Okay, so how do we calculate that? So we use this nice equation from your book. So equation 5.1 says that the percent by mass of an element is equal to N. N is the number of moles or the number of atoms. We're going to use it as the number of moles when we get to chapter 11 for sure, probably sooner than that. But for now, we'll call it the number of atoms, sorry. So it's the number of atoms in one molecule of the compound. And that's the number of a certain type of atom. So for example, the percent composition of hydrogen peroxide is composed of hydrogen and oxygen. So we take 2, so hydrogen peroxide is H2O2. We have 2 atoms of hydrogen in one molecule of hydrogen peroxide and 2 atoms of oxygen in one molecule of hydrogen peroxide. So we take those 2 hydrogen atoms, multiply it by the atomic mass of hydrogen, and divide by the molecular mass of hydrogen peroxide. So 2 times 1.008 AMUs for 1 hydrogen atom, divided by 34.02 AMUs for the hydrogen peroxide molecule. Okay, and then we multiply by 100 to get a percentage. So there is 5.926% hydrogen by mass. So percent composition is almost always going to be written as by mass, at least in our course. So there's 5.926% by mass of hydrogen in hydrogen peroxide. And what about the oxygen? So we do the same thing with oxygen. There's 2 atoms in one molecule. And we multiply by the atomic mass of oxygen, which is 16 times bigger than hydrogen. And we divide by the molar mass of the molecule, or sorry, molecular mass of the molecule. I apologize. Multiply by 100, and we see that it is 94.06% oxygen. Now, you might not have guessed that because we have 1 hydrogen per every oxygen atom. So like it could be like 50-50, right? No, because it's based on the mass, oxygen has a mass that is 16 times bigger, about 16 times bigger than hydrogen. So the percentage that it takes up is about 16 times bigger. I'm not going to calculate that exactly for you, but you can see that it is quite a bit bigger, even though you might not have expected that, and that's because this is percent composition by mass. Alrighty, you can also do this with empirical formulas. So we could have done this for hydrogen peroxide using the empirical formula instead. It's the same setup, except we divide by the formula mass and we use the number of atoms in the empirical formula instead. So the empirical formula for hydrogen peroxide, we had H2O2 as our molecular formula. Our empirical formula is just HO. So there's one hydrogen, one oxygen. So now we do 1 times this atomic mass, but we don't write that because it's just 1. So it's just 1 hydrogen atomic mass divided by the formula mass, which is not 34, but is instead 17, because we've got 1 from hydrogen and 16 from oxygen, so that's 17 AMUs, is the empirical formula mass for hydrogen peroxide. So 1 divided by 17, it actually gives you the exact same percent that we had before. So 5.926% hydrogen and 94.06% oxygen. So you can do it either way, you'll get the same answer. The percent composition doesn't depend on whether it's the empirical formula or the molecular formula. And we'll see why that could be useful in a little bit. All right, so let's practice. So you guys can pause here and practice and see what you get. We want to determine the percent composition of each element in chromium 3 phosphate. So chromium is a transition metal, so we give it our charge in Roman numerals in parentheses, and phosphate is one of our polyatomic ions. So you have to remember that phosphate is PO4 3 minus. And that's why chromium 3 plus goes along with it, and there are no subscripts on our chromium or our phosphate ion. Anywho, that's our naming and formula convention from last time, but now we want to focus on the percent composition. So we were given the molar mass of chromium phosphate, which is great. We don't have to look that up. So we do, however, need to know the atomic masses of chromium and phosphorus and oxygen, because we want the percent composition of each element. And if we pull out our handy dandy periodic table, we can look those up. So chromium is number 24 on the periodic table, and chromium has an atomic mass of 51.996 AMUs per atom. Phosphorus is number 15, and it has an atomic mass of 30.974 AMUs. And oxygen is our trusty 16.00 AMUs. All right, so now we have our atomic masses, we have our molar mass, and we have our molecular formula, so we have everything we need. So the percent composition, we'll start with chromium. There is 1 chromium atom in our molecule, so our percent composition is going to be 51.996, and we don't need to multiply it by 1 because we'll get the same thing. AMUs divided by 146.97 AMUs for the whole molecule. That's our molecular mass. Sorry, these are old slides. Should be the molecular mass. Oh my goodness, what happened? sorry, molecular mass, and that should be in AMUs. I apologize. I'm getting ahead of myself. And then we multiply by 100 to get a percentage. I'm going to write out the rest of them here as well. So there's 1 phosphorus. So we're going to do the same thing. We don't need to multiply by 1 because we'll get the same thing. So 30.974 AMUs divided by 146.97 AMUs times 100. And finally, oxygen, there's 4 of them because we got a subscript of 4, so we need to do 4 times 16.00 AMUs divided by 146.97 AMUs times 100. So let's see what those percentages are. Whip out my calculator. All right, so this first one, I got 35 point, let's see, we should use our proper sig figs, and we've got 5 sig figs in both of our numbers here, so I'll do 5 sig figs. We got 35.379% chromium. All right, what about phosphorus? So 30.974 divided by 146.97 times 100. And that gives me 21.075% phosphorus. And lastly, our oxygen. So 4 times 16 is 64 divided by 146.97. So 16, I'm just going to give it 0.000 so that we have the same sig figs for everything. So that one's going to be 43.546% oxygen. So we have mostly oxygen, which is what we might expect based on the formula, but not quite the percentages that you might have guessed based on the formula. And again, that's because we're looking at mass and not just the elements in general. Okay, so our answer is 35.379% chromium, 21.075% phosphorus, and 43.546% oxygen. Cool. All right, let's keep moving.